Hello. So yeah, we can continue. Are you with me? Yeah, thank. So actually, technically, since we have started from the 10 actually, so it need to change it. It's 2 hour is there. So this is basically the image compression. So more or less, see if you see now actually the communication part has come in picture. Communication, if you recall, see these type of different encoding schemes are there, different decoding schemes are there, digital communication. So this is actually related with that part. One, it is a part of the image processing, image, this one. But whenever this compression is there, this encoding, etc., this becomes part involve the communication. This I hope you would have gone through this Huffman. Have you gone through it? Huffman coding, arithmetic coding, run length coding. Are you aware? Yeah, okay. And what about others? Are you all even we will take up this? Yes, okay. Even see we will take up this thing in our afternoon session where we will take up the mathematical thing in the detail. No problem, Lakshmi. We will take up. We'll take up, and this course is self-sufficient. We don't assume that you only one prerequisite that you are present and you want to learn and you are present. That is sufficient. So now see coming to the types of image compression. Basically, two types of compression are there. One is basically lossless, another is the lossy. This is very famous interview question. Whenever so, what do you mean by the lossless is here you does not lose any information, right? So this is basically run length encoding, Huffman coding. This is Lampersiv coding. In the lossy compression, here you loses part of information in a controlled way. Remember your JPEG, MPEG, MP3, these all are basically the lossy compression. Even when we are saving the video in this form, we are losing the information. But it is not that significant enough that it creates a problem for us. Now, see, coming to the part, see what is basically this thing of man coding. Where is the role of the Huffman coding? Just we have seen it that first we remove basically the interpixel redundancy, then we remove the redundancy by the quantization value, which are rounding off, and then thereafter we quantize the output into a fixed. So here see when we are saying basically that quantized output into a fixed length code, which are transmitted. So there actually it is a Huffman coding is there. So this is basically the most popular technique for removing coding redundancy is Huffman coding. When coding the symbols of an information source individually, Huffman coding yields the smallest possible number of code symbols per source symbol. Huffman coding is a variable length coding and it achieves error-free lossless compression as it is reversible. It exploits only coding and interpixel redundancy to achieve compression. In terms of the noiseless coding theorem, the resulting code is optimal for a fixed value of n. Subject, so what do we do here? That code symbol we coded, the length of the code should be inversely proportional to its probability for occurrence. So when we will take up the example, these things will be much more clear. So just we are going through it, have some detail. Let's sort the symbols according to decreasing order of their probability. Then combine the lowest probable symbols to form a composite symbol with probability equal to sum of their respective probabilities. Then repeat step 2 until you are left with only two symbols. One. Then extract the keywords from the resulting binary tree representation of the code. Thereafter, we are able to capture. So this is the example that has been shown for the Huffman tree actually, so we can understand see what is going on here. So what is given? See A1, these symbols are given. For example, A2, A6, A1, A4, A3, A4. See how they are arranged basically. If you recall in communication, we read it, they are arranged basically in the descending order. See, note down here. So thereafter, see what do? We have arranged it. A1, A2. So how we have arranged it in this. So now what it has been shown here that is 40, this is 30. So what it's been saying, it is basically normalized. PDF we have calculated. So this is 40, etc. This is point. This is basically 100 only. 40, 30, 70, 80, 90, 100. That we have done upon 100, it has become 0.4, etc. What we have done, combine the, then what we do, combine the lowest probable symbols to form a composite symbol. What we have done, so these last two values where this is very less, so we will have combined it. And thereafter combining, we are getting this figure again. So what do we observe here? Then 0.1, actually all the value will be same here. But again, the last, this 0.1 and 0.1, they will made up the 0.2 and it will go here. Now this 0.1 and 0.2 will make the 0.3. And this 0.3 and 0.3 will make up the points. And this is a point. So now you see this change in the direction of the arrow. So how it has been, so this has been basically the there. So what we have got it, first we calculate the L average. L average is basically 0.4 into 1, 0.3 into 2, plus 0.1 into 3, 0.1 into 4. This is 0.06 multiplied by 5, 0.0 multiplied by 5. So what is this quantity? L average basically probability R of K that is multiplied by L R of K. So here see what we are writing here. See L is given, P is given, that is fine. There L is basically the length of the R of K, and so what it has been shown here that length R of K, and then you need the entropy. In entropy, basically when you multiply with the P R of K multiplied by log 2 P R of K, and it will be computed. This is how they have calculated. This is basically bits upon symbol. So what is basically the efficiency? Efficiency is basically H upon L average. So that you have calculated. So H we have already calculated here. There is entropy upon this one, L average. So that is basically point. So that is the efficiency of this one. What is compression is? That is B upon B dash. What is B here? B is basically 4 into 4 into 8. And what is B dash? That is basically the L average, 2.2. That is, we have calculated R equal to 1 upon 1 minus CR, that is 1 upon 3.63. So that way the redundancy is 72%. What about the run length coding? The in run length coding, see, is one of basically simplest lossless data compression tech. Reduces the interpixel redundancy. It consists of replacing a sequence of identical symbols by a pair containing the symbol and the run length. It is used as a primary compression technique in the 1D additive group 3 fax standard as the computer icons and congestion of the techniques in the JPEG compression standard. Here you scan the image horizontally or vertically, and while scanning you assign a group of pixels with the same intensity onto a pair. So again, we will also see its examples so that we can understand it, that what it is going. Again, see here some string is there. So when we are saying see it is run length coding, so as we have seen it, that it basically reduces the interpixel redundancy. For example, you notice it here. So what we have written, see for example here, this digit is given 6 times 5 has come, 4 times 3 has come, double 3, 2. What we have done, we have written the 5 in this way, 5 multiplied by 6. And this is 4 3. So what we will write, we will write basically encoding a string against it is basically here. So how will we write this complete number? That 5 6, because 5 is there and it is 6 times it is repeated. What about the 4 number? 4 is basically 3 times repeated. 3 is basically 2 times repeated. 2 is repeated basically 1 time. Even it is not required. So what has been showing here that it is 12 bits B upon B dash. So what is B dash here? B, B dash is here. Again, you will calculate all these bits and you will get this way. So in another example, we can take it where numbers are repeated. It will be always useful when the same number is repeated. So here 1 is there, 1 we can write 1 of 13. Here 0 is there, it is 7. And it is 1 is there, so 1 9. So I can represent that number into a very, very small way. So what we can write it here. So this is basically this what is written here. 1 is basically 13 times, 0 is basically 7 times, 1 is basically 9 times. What it is being written? See, 1 is there, this one, and this 1101. What is this value? This one is 1, this is basically 2, 4, 8, it is 30. It is 1, it is 30. Now you, what about this number? Here it is 0 and thereafter it bits, it is 7. Here it is 7. In the same way, here it is 1 and here it is 9. What is CR actually here? CR is basically 29, it is upon 50. So So how you are doing it? So you have already earlier calculated is 13 plus 7 plus 9. It is 13 digits plus 7 plus 9. So it was actually the 29 bit. But now it has been simply represented in form of the 15 bit. How much reduction is there? So that you can calculate. It is almost the order of the two. Is this problem clear or any question? Run length coding. Okay, clear. So anyone see if your question? It's again like the communication technique. So then where are you finding problem? No doubts. Okay, fine. That is the thing. This was so what you see, one thing is very clear that when 29 bits were there, the bit redundancy is there. We simply write it, it will lead to the 15 bits. So that much redundancy it is there. It is almost this much amount, almost the half of the amount. So now coming to the another example of the run length coding, again you take the image part. So this is basically image 8 by 8 image 1, 2, 3, 4, 5, 6, 7, 8. This is also 1, 2, 3, 4, 5, 6, 7, 8. So this is the given here. So what is basically the CR here? Can we easily calculate it? Yes, we can very easily calculate it. So how many times 4 is there? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is come as 9 times. Thereafter, what we are writing that 5 has come 5 times. 4 has come 3 times. So what we are doing here we are doing basically top to down scanning, right? Top to down scanning. So that's why it is 4, 3, and then it is 5, 1, then it is 6, 3. And thereafter, what we are seeing it is 20 pair. 20 pairs means basically 40 number. And if we do the horizontal scanning, see, you can also do the horizontal scanning. Horizontal scanning will go in this way. So what will you get? 1, 2, 3, 4, 5, 6, 7. So 4, 7 times, then 0, 1 basically, then thereafter 4 is 1 time. So there are the two ways. So what we see that it is basically the minimum pairs is basically 40 number when we do the vertical scan. What we are getting, so if we are getting the compression ratio when we are going toward the top down scanning. So here we conclude this part, this coding part. Now we come to the another topic, morphological image processing. So what we have seen in the basically image compression, that at the different type of whether it is the interpixel redundancy or it is the quantization, or it is the coding style, different coding style. The codes can be reduced and the compressed image can be obtained. This is the one. So can we move towards this topic, morphological image processing? Fine. So now see, what do you mean by this morphological, right? Morphological is set of the image. Now we have also covered the image compression. We are now basically covered a very basics part, then basically the image enhancement, then the image compression. Now we are going to the morphological image processing. Morphology is basically broad set of image processing operation that process binary images based on a structuring element or kernel which decides the nature of operation. In morphological, each pixel in the image is adjusted based on the value of other pixels in its neighborhood. So, how will we do it? See, here, pixel value is adjusted. That we will see. What happens in the morphological? It is a dilation, it is erosion. That part is closing, that part is gradient, that is stop at, and that is black at. So, all these things are part of the morphological image. So, coming to the first part, so what is so morphology, as we say, see, they basically work upon the binary images. What do you mean the binary images? Binary image basically the black and white image, right? What do? You basically structure the element, right? So again, so this you see the dilation. What do you do in the dilation? Dilation is basically a morphological operation. It's a black and white. Yes, it is black and white that add pixels to the boundaries of foreground object, right? In an image. What what will it do? How does it work? A structuring element slide over the image. If any pixel in the structuring element overlaps with a foreground pixel, the corresponding output pixel is set to foreground. What we are saying here that if any pixel in the structuring element overlaps with a foreground pixel, the corresponding output pixel is set to foreground. So now see what is going on in dilation is process of expanding image. It is increased basically brightness of image. So what is basically mathematical expression? It is A is there plus B is there, and it has been shown here that it is original image and this is structural image. So how the dilation will take place? So for example, we want to multiply it. See what is this operation? So what we are doing? It is 0 1 0 this one, and here it is 1 1 0 0. So first line when we will multiply it, so what has been done here? So first this is the example here 1 0 1 0. This is the original image, and this is a structural one. So in the origin, see what you are doing. So once you have multiplied it here with 1 here, so what will happen when it will multiply 1 here? This will cover this part. So you can, this one is basically coming here, right? Thereafter, it will multiply with this one. When it will multiply with this one, what will happen? This one will coincide and this one will be outside. So what has been shown here? So in the third part, see what has been done here. So when this 1 is there, so when you will multiply, see this block, this 1, when you will multiply with this one, so this one will come here and this one, this structure will replicate here. This structure, which was the origin, it has been repeated here. Thereafter, what we are doing, thereafter we are getting the 3, 1. Now we will go to the second row. When we will go to the second row, again when we will put this 1, 1 with this one, so what will happen? This one and this one. This will take the boundary, and what you will get? You will get now when it will be multiply with this one, since this one has come, so again when this structure will come, so that's why this structure is coming. So now thereafter, so this is the way to do it. What do you mean by the erosion? Erosion is basically that remove pixels. So what is happening here in dilation? Dilation, if you see what is happening here, that add pixels. Here, see if you see it is bit thin, and here it has become more thicker. Whole white region has been boundary has been added and it is bit extended. It is that has been told in. Now come to the part erosion part. See from the word itself, erosion it basically that removes pixels from the boundaries of foreground objects in an image. What do we do here? See that's why see if you see the sign also it is here. And this is A plus or B. So what we are doing, so here actually it is a subtraction. So what we are in this subtraction, if you see here, this is A minus B that has been there. So what is the resultant part? It is J. So it has become thinner. Earlier it was there, so now it has become thinner. But what is important part, see when this is the original image and this is the structural part which is subtracted. But finally, whatever the part is there, it will always belong to the A only. It is So this mathematical expression is their output become foreground only if all pixel, otherwise pixel is removed. That has the opposite process of dilation. Image shrinking is obtained. So what we are doing in this part, this is origin. So this is original image is there. When you will multiply the structural image, so what you will get? You will first this is there. This is one. This is all the one is there. When you will multiply this, so this is here image shrinking is obtained, and so what we are doing, so structural image, so that has been applied here. This way. Another case is basically related cases opening. In opening, basically, what do? You basically do the morphological operation that removes the small objects while preserving the overall shape and size of larger objects. So which one will be removed? These small dots are there that you can see. How it works, basically here, erosion removes a small unwanted foreground pixel, then dilation restore the main subject shape. So mathematical expression, that is basically what is it? It is erosion followed by the dilation. It has been, this symbol has been shown here and this is plus B, it has been shown. So here this is basically opening here. So this is basically our structural image is there. This is original image. So this is A minus B. So what you are doing here, again see here you are basically subtracting. A minus B, you are subtracting this part here. When you are subtracting it, it has become with this central element, other elements have been subtracted, other part have become zero. And then when you will take it in the your neighborhood, there also you again take it and it has become, and this is another operation is closing. Closing is basically morphological operation that fills small holes and gaps inside foreground objects and smooths their boundaries. Here see what is in the closing, basically here dilation is followed by the erosion. Opening actually, erosion was followed by the dilation. If you see here, erosion is followed by the dilation. This one. So what about the top head? So this is the gradient before it. Gradient, basically morphological gradient, extracts the boundaries of objects by computing the difference between dilation and erosion. This is the thing when you will check out the procedure, you will get this thing. Dilation basically expands the object, erosion shrinks the object, and subtracting them highlight only the boundary region. It has been shown here. This is basically the dilation. This is basically the erosion. And then subtracting them highlights only the boundary region. Top hats. The top hat basically extracts the small bright objects from image that are smaller than the structuring element. Top hat basically the input image minus opening image. So opening image basically smooths the image and removes the small bright regions. Subtraction recovers those three bright features that were removed. What is the black hat? Black hat basically, if you see the diagrams, they have black minus hat when we have done it. So what does it do? It basically extracts a small dark object or gaps that are smaller than the structural element. So how it works basically, it basically close, fills tiny dark holes and smooths the object. Subtraction retrieves those removed dark regions. So you have seen it here. This board is there. When you use a black hat operation, it has resulted into this. So now we come to the part C, image segmentation. Image segmentation is a computer vision technique that partitions into discrete groups. So for example, see when we go for the brain tumor detection, etc., whether it is of the some say some whether it is some problematic in nature, benign or non-benign. So that all can be obtained if we are able to first segment the image. There we will do this image segmentation. We stop it here because again, see, it's another new topic. It's a bit of covering so many. Better we and if you have any question. What I any question from your side? Actually, see, these are all bit mathematical. So in afternoon, definitely we will take up the examples and we will go through it. So it will help you. I think too many topics we have covered. So this is threshold image segmentation. This is image segmentation can be based upon the discontinuity, it is similarity, it is edge based, as it can be gradient based, it is Gaussian based, in gradient it is sober, Robert, private. In Gaussian it is canny edge detection, Laplacian. Laplacian or Gaussian basically we have been taking the differences of the partial differentiator. Thresholding global and local, region based basically region growing, region splitting and merging. Going threshold based segmentation is an important technique basically for image segmentation. Produce uniform region based on the threshold value criteria T. So I think we will go over it later so that thresholding and after threshold, then multiple thresholding, adaptive thresholding, region growth, region split, merge segmentation, P means clustering, P means clustering. So you'll go through it later. I think better that it's a continuous topic. Otherwise, we have to leave in between. Any It's a long journey. And anyways, you have a time, still your time is there. And these are very important topics. So still we have our journey. This is our one of the milestone. So that is basically on our, that is the fifth day. That is basically middle of the journey. Almost see. Today we will cover our. So actually we have covered more than half of the journey. Yesterday we took up the 1.5 hour lecture. So we have crossed our middle mark. So we are now yet to reach. We are near our destination. Right. See, just one thing, see on how many it will be convenient on the, see, another thing we are planning that 24 December, we are planning to conclude on 24 December. Since 25th is the actually holiday, so many people are in a mode to of transition. So we are planning to shift that 2 hour also into our another sessions, which is on the 24th of December. We are thinking that we will conclude it in the morning of the 24th only. Will it be, can we take up that extra 2 hour or we can put it there as per your convenience? See, what I'm saying that instead of basically 24th December, because that is the day when people would be leaving. On 25th, actually, almost everywhere it is holiday and it is some winter break, etc. We are planning to conclude in morning session, basically at 1 p.m. So see, what is the thing then that 2 hour that basically we initially planned that 2 hour that we can substitute earlier. So one is option that we can today, for example, as we have extended slot, we can also do it tomorrow also. One hour, 1 hour in the morning and 1 hour in the afternoon. It finds it. So what we can do, so what tomorrow we can have the class in the basically from actually 10:30 or can have the class from 11 to 2 and then 2:30 to 5:30 or we can have 10:30 to 1:30 and then 2:30 to 5:30. Will it be convenient? One hour, 1 hour extra. Okay, 10:30 to 1:30. Okay, that we can do. This is fine. We can, okay, this is Okay, we take the session earlier. Definitely. So this is final, right? It's 10:30. This is fine. That is for tomorrow. And so we will conclude our session. So our last lecture will be in the morning. We will conclude our course between 11 to 1 p.m. on 24th of December. So you will be free in the afternoon session. Okay, fine. Thank you. We'll come back. It's actually short break. Today also we are planning to 2:30. So better we conclude it here, and whatever question we will take up it. I hope it is not too fast. Thank you.